Good morning. Let us start. So, last time we just got explained the CC alpha, CC beta. I asked you to reflect at home, because this is a difficult topic, and I promised that we will start with it this time. So now I'm waiting for your numerous questions. Okay, apparently no questions. In any case, you can also come back to this later. If still you don't understand, you can ask at any time. And then before the exam, we also will have the tutorial hour, or actually most likely several tutorial hours, because your exam times will be spread across quite a long time probably. So at any moment, I'm ready to explain again. But now let us then look at the big picture. Let's sort of conclude with this. Yes?
Before we start, I had a question about the homework with the complex analysis. So I wasn't quite sure how to calculate the recovery for the recovery, the parts when you subtract the one that is accounting for the sample preparation and stuff. I'm not sure where to get that value from, and how to calculate it. Could you explain that better?
That will come from replicate measurements of the same sample. So try to look up in the text a place where there are either the values or some information given. So replicate measurements of the same sample. And if you now go through the text again, you still don't find, come back with the question then tomorrow, and I can give maybe a bit more hint. It certainly is doable because it hasn't changed for several years. It's the same exercise, and also among the people here in this year's course, several already have completed. So again, I will, if needed, give more information, but let's stick to that at the moment. Try to revisit it and come back if you still don't know. Okay, now about CC alpha, CC beta. This is a kind of a comparison table. What these values tell us, and as you see, they have different purposes, they apply to different things, and they tell different things. So CC beta, if I start with beta here, CC beta characterizes your analysis method. With CC beta, you tell your customer that, yes, this is the concentration level I'm able to detect. And if we put it rigorously, I'm able to detect in 95% of the beta value is 0.05, as it usually is. So this is something with which you characterize your method, and it addresses the actual analyte concentration in the sample, as I have explained several times. But CC alpha you use for interpreting an obtained result. So this one does not work with actual concentration in the sample, but works with your value, the value that you got from your analysis, and now you need to decide whether this is okay or not. So you interpret the obtained result. If it is above CC alpha, then either depending on whether there is maximum permitted limit, If it is above CC alpha, then either if there's no maximum permitted limit, it tells yes, the sample is contaminated. Or if there is the maximum permitted limit, it tells yes, it's above the limit. Okay. Now, connected to this, yeah, as I actually already said, you are comparing your result with CC alpha. But with CC beta, you compare what are customer requirements or legal requirements. So customer requirements or legal requirements are compared to CC beta, meaning if legal requirement is that limit of detection or CC beta has to be less than or equal to like 0.5 micrograms per kilogram, then this is exactly what you use it for. And you are essentially saying that, yes, in 95% of the cases, I am able to detect 0.5 micrograms per kilogram if your CC beta is 0.5 micrograms. And CC beta aims at assuring that your method is suitable, meaning that it has sufficiently low detection. But CC alpha aims at protecting a consumer or a person somewhere outside. So the person who might drink the water or use the soil or eat some fruit or whatever. So CC alpha avoids damage to the consumer, avoids that people will drink something that they are not supposed to drink or eat something they are not supposed to. Whenever it is CC alpha, CC beta reported, the alpha and beta have to be specified. Let me for a moment come back. With CC beta, the beta value is almost always 0.05. With CC alpha, with CC alpha, sometimes it's 0.05, sometimes 0.01. We did in our, or we do in our example and in our calculation, we do with 0.05. But usually it is so that if something has a permissible limit, it is then 0.05. But those that really do not have any permissible limit are oftentimes 0.01. But this comes from legislation. This is again something that you don't need to invent, but in cases when you can assign it yourself, then I would probably go for 0.05 in all those cases. But in any case, whenever reporting CC alpha, CC beta, these values have to be specified. Any questions? If no questions, then let us now revisit our calculation exercise. Because you may remember we did not calculate CC alpha and CC beta. Me perhaps. And now I'm going to share the file. By the way, has anybody tried this solved Excel file? Can you open it from the Moodle? Be accessible from Moodle. Can be, okay. Okay. So we need to fill in these two slots here. And now those of you who are in the room, you can still see the slide number 37. Those of you at home, you cannot see, but you know what slide I'm talking about. So let's see, here in slide 37, we see how CC alpha is calculated. The formula is here. First of all, we need average concentration found from the blanks. What is it in our case? 0, yes, we have written here explicitly. No? Oh, we run equal to 0 plus. Okay. Now we have to put 1.64 multiplied by S blank. In this case, we did not do blank experiments, or we did not do experiments with the blank. So we essentially simply assume that these concentrations are suitably low, so that their sort of standard deviation can be used instead. Where could we find it?
From the Linest function.
From Linest function, and where exactly?
Standard error of the y estimate.
Say it again.
Wait. The standard error of the y estimate below the standard deviation of the intercept.
One?
To the right.
This one?
0.45.
Yeah, exactly. So this big S, or the standard deviation of the regression, as it is sometimes called. But now you see the standard deviation of the regression has units of the signal. But here we need to have concentration as the unit. Yeah, so we see here the unit is concentration unit. What shall we do about that? Sorry?
Divided by the slope.
Divide by slope. Yes, exactly. So slope acts for us as a unit conversion factor, if you wish, or a sensitivity conversion factor. So we do essentially the same thing as we did here. Yeah? The standard deviation divided by V or the slope. Okay. Oh. Up. And 1.64 I forgot. Let's put also 1.60. So now you have this kind of formula. And you should see something like 0.07. Let me put some more decimals here so that you can better compare. Did you get the same? 0.0709.
Like in this case, we will always use this S, or like I didn't get why the standard, what happened here with the repeatability of the blank, like why we are using in this case.
We should use repeatability of the blank if we have that information. Yeah. The same is true also in principle for limit of detection. Yeah, like the ordinary, how you ordinarily detect the limit of detection. But this ICH approach of LOD uses this standard deviation of the regression divided by B with the assumption that it was done in matrix and that the concentrations are all very low. It uses this as a substitute for the standard deviation. So it's a kind of a proxy. Let's put it that. Approximation. I think it's a pretty good idea, actually. I don't think that missing the blank analysis data here is a big problem. But what is a problem is that we should have more points in the very low range, which we don't have. This now leads to some extent to the overestimation of LOD, get higher than. All right. So that if your analysis gives result 0.07 or above, and if this analyte is something that is forbidden, then you shout, contaminated, contaminated, don't drink the water. You don't compare with 0.14, but you compare with 0.07. If it is above 0.07, you ring the bell. Okay. Now, CC beta, if you remember, was calculated by CC alpha plus exactly the same term as we already have. So that I can even, as I'm doing, I can even copy this phrase and write like this, equal to this one. So that with this method, you are going to tell to your customer, look, if sample is contaminated at the level of 0.4 T, I'm using rounded number now, yeah, 0.14, then yes, we will be able to detect with 95% probability. However, if we get result above 0.07, then already at that level, we can be 95% sure that the sample is contaminated, and we will ring the alarm. Now, if you compare CC beta to LOD, what do you discover? The essentials. And this is, as I explained to you last time, 1.64 multiplied by 2 will give you 3.28. And 3.28 is essentially the same thing as 3.3. So that, as I already said in the beginning of this section of the course, for all practical intents and purposes, LOD and CC beta are synonymous. But CC alpha is something completely different, and LOQ is also different. So now you are equipped with knowledge also for the last homework. That now you have no obstacles for completing all the homeworks. But of course, yeah, if this complex analysis is problematic, as Ola said, yes, okay, we can, if needed, look into that. Okay. As we already discussed, what could be done differently, I don't think I need to repeat. But what we did not discuss is this question. What is the sensitivity of the method near the LOD? See how would you answer this one? what is the sensitivity of the method near LOD? In my opinion, this is an extremely simple question if you think what was the definition of sensitivity, but let's see how you address that. Nobody wants to tell me. Helvin says the slope. Yes, sensitivity is quantitatively evaluated by the slope. Yeah? So we can even do it like this, that we simply copy this. Copy this. Yeah. Sensitivity. Yeah, sensitivity has a unit. Important. Yeah, like slope has a unit. And equal to, and we can again simply make it very easy. And again, the critique might be that we rather should have data points just here, ignoring these data points altogether, having data points only here, and then examining the slope would be better. So, can we now close this exercise, or is there anything you still would like to discuss here? Okay. Apparently, no other discussion topics or discussion points. Then I will take the rights back. And yeah, we looked at this. And now one more thing that might need to be explained is that this whole thing does have some assumptions. No? First of all, the assumption that the distribution is the normal distribution. Not always true, but okay. Not always true, but all the mathematics, as you saw, originates from the properties of the normal distribution function. And you really have to make some replicates in order to get some reasonable estimate of standard deviation. And even if you do replicates, you still, your LOD still will most likely be very changey, meaning on different days you will have different LODs. Then you should not determine LOD in calibration solutions, just the solvent and the analyte. It should all be in matrix. Here there are different possibilities possible. For example, you can do so that you do the sample preparation with the blank matrix, and now you get the solution which contains all those matrix components, and then you add the analyte, carefully added amounts of analyte, which I think is mostly done, and this is very, very appropriate. But in any case, all those potentially interfering compounds, the noise, everything must be the same way as in your real sample. If you do it just in clean calibration solutions, you will not be getting. Also, systematic effects are here largely neglected. This is almost inevitable. So we do not speak of any biases or anything like that here. And often what are additional assumptions that we also did, we assumed that standard deviation is the same at CC alpha and CC beta level. This is not necessarily always true. But this 3.3 in calculation of limit of detection actually has that implicit assumption, because it's like 1.64 plus 1.64. Yeah, so essentially the same standard deviation is used in both cases. Also, sometimes repeatability is determined under constant analyte concentrations, sometimes not. The way we saw here now, it was not constant analyte. It was the ICH approach, which rather has different concentrations, but they are all focused down in the LOD range. It also is possible to do with different approaches, that you don't do it like calibration graph, but you do simply like replicate analysis of blanks or very low concentrations. So there are different approaches. Like I said, for LOD, there are different approaches. There are also different ways of how you can evaluate CC alpha and CC. And if you need more technical guidance, okay, how exactly do I do, or especially if you are obliged to work under some specific validation guidelines. So suppose you end up in the, like, let's say in the United States and working in drugs area, then you have to follow FDA recommendations or FDA requirements, then you should look into those guidelines specifically. And I very much recommend this Hanno Evard and etc. paper, part 1 and part 2. They are both cited here in the slides. Although this is now already 9 years old, but it's still very relevant. The big picture is very well given there. So if you are really interested of the big picture, how LOD should be handled or can or should be handled, then this is a very good place to start. True, it again, like different our things, it is centered around LCMS. But if you happen to be doing ICP-MS or maybe some neutron activation or essentially any technique, you still will find it helpful. It's not so much LCMS centric that it would be unusable by others. So, and this would end the LOD, LOQ part of this course. If you now have questions about those, please ask. Okay, if not, then the next part is to a large extent repetition. Here are now all those, let's call it error-related characteristics, yeah, precision, trueness, accuracy, and all those things, which we have already discussed at length. So that here we largely repeat. And the reason why I'm not giving any homework on this, and why actually there's so sort of very little homework on validation, while validation is so important thing, is that actually several of your homeworks already have addressed this. We've done already precision quite a bit. Yeah, you have done homework for determining recovery. Again, like bias or trueness related parameters, so that you already actually calculated those things. But we still go through them. So here, you've seen this, I've explained this. Let me not explain at all. Let me simply ask, should I repeat anything? You should already know pretty well, and you've probably seen it in different courses and so on. Any small questions, anybody? Maybe some nuance that you would like to confirm? Probably not. Yeah. Okay. Then we try to go through some of the things, although you've already heard this. So precision is related to closeness of agreement between indications or between signals, which you obtain by replicate measurements of the same or similar objects under specified conditions. Can anybody tell me, you've heard a lot of this, what the specified conditions are in the case of precision? Depending on specified conditions, we speak of different precisions. It's a vague type of question. But you have the knowledge. You maybe don't know that this is what I'm asking. Okay, let me ask it the other way. What precisions have we looked at in this course? Within lab reproducibility, okay. Repeatability. Yeah, intermediate is the same thing as within lab reproducibility. Yeah, but yes, correct. And then there was one more which we also have sort of, there are several more, but one more which we have paid some attention. Uncertainty is different because uncertainty also involves systematic effects. But with precision, systematic effects are not involved. There was one more precision that we, not so much, we did not discuss it much, but still we, sorry? Yeah, reproducibility, and please say one more phrase into this. Sorry? Between lab reproducibility, yes. And these things that determine which of these we are talking about are these specified conditions. In repeatability, what were the specified conditions? We determine repeatability. What are there the
Scatter of the data, like obtain it in a single day?
Same day, the same person, the same calibration solution, the same instrument, etc. So everything is as same as you possibly can. Okay. What were the specified conditions for intermediate precision? Christian has also, sorry, Christian, I did not note this earlier. Elvin, yes, same analytical run, correct, yeah, for repeatability. But now for within lab reproducibility, what are then the specified conditions? But what should we keep constant? What should change? Different days.
Like common things that will change in a lab.
Exactly. Yeah. There can be different calibration solutions, different like solvent batches, different solid phase extraction cartridge batches. Maybe the detector has been maintained at some point, column has been exchanged. If the same analysis in that lab is done by different people, then also person can be different on different days. So all those things that normally change. And if we speak of between lab reproducibility, which true, like Ba-Long said, is oftentimes called simply reproducibility, then it's different labs, yeah, so that so much can be different. Occasionally it is specified that it should be the same method, but almost never you find two different labs which have absolutely the same method. There are always nuances. And you can determine it with any example. You don't need to have any reference value, as we've frequently noticed. And if it is the precision of the method, not just the precision of the instrument or the precision of the detector or the precision of the determination step, then all method steps have to be included. Meaning, if you do 5 replicates, it's not so that you take one batch of soil, do the sample preparation, and now disperse it into 5 cubes. No, you take 5 samples. Of course, they have to be identical as closely as possible. You do 5 times the sample preparation, etc. So everything is done 5 times. And of course, I probably don't need to repeat, typically expressed as standard. And now trueness is about the agreement between the average of an infinite number of replicate measured quantity values and the reference value. Of course, in practice, you never have infinite number, so that it's simply many values. The typo here, Ferrer. Ferrerens. New word invented. Yeah. So here we do need reference value. Precision we did not need. And we have looked already at 4 ways how reference value can be obtained. Can be certified reference material, independent method, analysis with independent method, proficiency testing sample, or spiking or formulation. Make artificially. And you again need to do replicate measurements because you want to get rid of the random effects. You want to evaluate with trueness only the systematic. So that here it says, of course, infinite number of replicate measurements. In practice, it of course never can be infinite number, but it has to be sufficiently large. How large is large? Very difficult to say. I would say that 10 is very okay, mostly in chemistry. 5 is sort of below 5, I don't. You can use this strange grading. 10 is okay, below 5 is not okay, and between 5 and 10 is sort of okay. Here you can use either bias or recovery for expressing. One is difference, the other is ratio. They are mathematically different things, but fundamentally express the same thing. And bias then can be absolute or relative, so that in fact you have even like 3 ways of expressing your trueness, or 3 ways of expressing how the systematic effect is. And finally, accuracy is closeness of agreement between measured quantity value and the true quantity. And this is really applicable to one particular value or one particular result that you have got. This is different from trueness, where you test the agreement between the average of replicate values. But in the case of accuracy, it also has to be applicable to one particular value. So how well this my result that I'm going to maybe present my customer, how well that matches with the true. Of course, we don't know the true value, so that instead of comparing it with the true value, which we cannot do, we do uncertainty estimation. And we express our value with uncertainty, and this tells the customer or anybody who is interested in our result, aha, okay, with some probability, the true value is within this range. With a small probability, it can also be outside. Big probability is inside. And about probability, you of course know how we manage that. Yeah, standard uncertainty, roughly 69%. K2 is roughly 95%. And if you want to be more sophisticated, you do the Welch-Sutherth-White. And typical expression of accuracy is measurement uncertainty, but it also can be evaluated. These are two different ways. So measurement uncertainty you can always use. You can use it for any customer sample. Customer gave sample, you give back result with measurement uncertainty, which is your estimation of how accurate the result is that you give to the customer. And for customer samples, you almost never have any estimates of true values. You have no idea what it is. Your result is the only thing that you can give. But if you do, or for example, if you participate in interlaboratory comparison, then eventually, besides your value, you will also have the reference value. Either it's consensus value or independent reference. Also, if you analyze a CRM, certified reference value, you get your value, and again, you can also reference value. And if you have a reference value, which is not true value, but is a very good estimate of the true value, then you can use EN value or zeta score for expressing your accuracy, essentially telling, okay, am I in agreement with the reference value or am I in disagreement? So that this second line you can use only in the case if you have some reference value from some. Simply do analysis for customers who just bring some samples and you have no idea how much is inside. And your measured value is essentially the only value that there is, then there's nothing else to do that just give the value with answer. And of course, both EN value and zeta score, they depend on your value and also your uncertainty. So that if you know how to measure, you are measuring well. If you know how to evaluate uncertainty, then your EN number and zeta score will be okay. EN number below 1 and zeta score below. Absolutely. Any questions? You've heard all these things in different contexts, but I'm retelling them to you in slightly different ways. So I haven't used really these sentences in all cases before, so that you make more connections in your head. I think fundamentally you probably did not hear much new at the moment. You've heard essentially all of these things from me already. Okay. This graph I have explained. Do I need to repeat anything, re-explain, explain from scratch, or answer some questions? I think you should know all this. As I said, it has already been, so I will not explain. Again, I'm happy to return to this. And now come the different precision types, which also we have already looked at. If you determine precision under the same conditions on the same or identical samples. We call this repeatability. And these conditions that everything is the same, these are called repeatability conditions. And also this is sometimes called within random. Repeatability is almost always determined for analytical methods during validation. In part also because it's very easy to determine, apparently from many other things. But let me now ask this question. You have information for answering this. When do we need to work under repeatability conditions? Different from situation where we simply want to determine repeat. So when do we work under? When it necessary? Interesting. Christian says, assessment of homogeneity and short-term stability. Yes, correct. Please explain, Christian, what that means and why do we need to use repeatability conditions in those cases? What you answer, Christian, is in principle correct. I think you have in mind the right things, but it's not really exactly worded in such a way that it's very like well understandable. Let's try to look at it this way. That if you now have a number of bottles, like this came up in certified reference material production, yeah? You have a number of bottles and you want to find out how much the concentration of the analyte varies between bottles. When you now analyze all these bottles under repeatability conditions, what happens is that there are two kinds of variabilities that come in. Variability from your method, variability from the difference between bottles. And your aim is that your result will, as much as possible, show only the variability between bottles and not the variability of your method. So you have to suppress the variability of your method as far as possible. Meaning, you have to use conditions where the variability is the smallest, meaning you have to use repeatability conditions where everything is the same so that variabilities are brought to a minimum. And in addition, there's something called ANOVA, or analysis of variance, which we did not address in this course, which enables like separating variability from method, variability from between bottle variability. This needs some slightly more sophisticated experimental design, not really very difficult. And actually, I even considered including it in this course, but I thought the course is already so packed with things that maybe let's not take that. But yes, in such cases, when you need to find out differences between something, you have to work on the repeatability conditions, so that variability from your method would be as small as possible. And this, Christian says homogeneity and short-term stability, but long-term stability is exactly the same. If you remember, we addressed the experimental design in long-term stability determination. Was there something called isochrono study, yeah? So that they were kept during different times, where the samples kept at different temperatures, but finally analysis was done with all the samples on the same day. Not so that you keep something for 3 months, then you analyze, others for 6 months, then you analyze. No, you manage in such a way that all the analysis is done on the same day. So this is again needed for achieving repeatability. Everything done on the same. Okay, it's pretty important. This might also very well be important for you in your future work. You might end up with some task where you have to do exactly that. Huh? Now, reproducibility.
For just one question. For the LOD and LOQ determination, do we need to work on the repeatability?
Mostly people do that, yes. And I would say that yes. Because under within lab reproducibility conditions, I'm afraid it would not really work properly. You would have like too much overestimated. That's a good point, actually. Did I not mention it? No. No, I don't have this. But of course, I said here phrases like you should determine LOD on different days, yeah, which means determine LOD today and tomorrow, then both of them will be within days. Yeah, so will be repeated. But I will put specifically in. Okay. Anything else? Anybody? Then, reproducibility. Here, as we have explained, you work under changed conditions. Huh? But the samples are still the same or identical. So this is the same. Yeah? It's either the same sample or identical samples. And this is like in general reproducibility. And the change can be different lab, analysis time, plus all the typically changing things in the same lab, and then possibly also other different possibilities. So this is the between lab reproducibility. And this one here is what I've been stressing so much in this course, is the within lab reproducibility or intermediate. The analysis is done on different days, and everything is allowed to change. That typically changes in the lab, but the method, of course, has to be the same. And the main items in the method have to be. So if some big thing changes, like, for example, completely new digestion system, or you, for example, you replace the sample preparation approach completely. You do sample preparation in a different way. Then this is so big change that it is already outside the scope of within lab reproducibility, because it's essentially a new method. Then you have to start from. And as we've explained, repeatability standard deviation is smaller than within lab reproducibility standard deviation, which in turn is smaller than combined standard uncertainty. Please tell me why. Why does this hold? Why does this hold? Maitane?
Because SRW takes into account the systematic effects that has become random during the long term, and also the combined uncertainty takes into account the systematic effects that remain systematic even in the long term, and also the random effects.
And SR, the repeatability, takes into account only
random effects, but also the systematic that has become random in the long term.
So this takes into account only within the random effects. This takes into account within random effects and those effects that are systematic within the but become random in the long term. And UC takes into account within the random effects, those that become random in the long term, and also those systematic effects that never become random at all. So that each takes into account something more than the previous one. So this is why they have to be like this. In this question in the box, I've already asked, but it's an important question, so let me ask again. Is the most likely reason if you suddenly get this kind of insufficient number of replicates. So if you don't, for example, only 3 replicates, then you can easily achieve this situation. 3 replicates, of course, is almost never sufficient number of replicates for any serious investigation. But it can be a sufficient number of replicates if you simply analyze routine samples. For routine samples, it also can be just 2 measurements per sample. But determining some effects for future use, then it's not. Now, this is a scheme that, again, you have seen. The short-term and long-term variabilities. In the short term, lots of effects are sitting in the systematic effects block, and not so many are sitting in the random effects block. But the longer term you look at, the less systematic effects there are, and the more there are effects that have changed from systematic to random. And typically the ISO-GAM uncertainty evaluation works in this long-term realm, and Nordtest approach works, short-term realm, and Nordtest works in the long-term realm. And it's always easier to determine random effects than systematic effects, because
we have trouble finding the true value or the...
Exactly. For random effects, you can use essentially any sample. Don't need the true value. So the more effects you have in this block, the easier, in some sense, your work becomes, or the easier it is to evaluate the uncertainty, which has to embrace all these effects. Why I'm saying that if you are not a guru and then maybe don't have a lot of time, yeah, but you have all these long-term data, yeah, like control charts and CRM analysis results, then Nordtest uncertainty might be more safe and in a way more like trouble-free than the ISO-GAN. I think here also I don't see what else. Any questions? Okay. Then we have now also reached the end of these error-related quantities. And now we look at ruggedness and robustness. Are also important parts of validation. These two are very short in this my presentation. They are very nicely, or can be very nicely linked with experimental designs, yeah, how you change different parameters and rerun the experiments and so on. And this is a very important and big topic, but again, simply impossible to fit everything into this course. So whoever is interested more in to learn more about this ruggedness, robustness part, you are welcome to visit our LCMS validation course, which has that part quite nicely, and also experimental design part separately there. You can learn quite a bit. So, oftentimes ruggedness and robustness are described or are handled as synonymous. Sometimes also difference is made. So I'll try to explain what is the difference that is sometimes made. But again, don't be surprised if in some guidelines they use robustness, in some they use ruggedness, and they might involve both of these things into one term. So robustness can be defined as characterizing method's capacity to remain unaffected by small variation of intrinsic method characteristics and sample matrix. These intrinsic characteristics are things that you can change. Okay, mobile phase composition, some detection, wavelength, column age, and so on. So in principle, you can deliberately change mobile phase pH. You can make experiments at different mobile phase pHs. And you can, the robustness, if defined like this, then robustness can also be applicable to separate characteristics. So you don't say simply that robust method, but you can say that the method is robust with respect to mobile phase composition or pH. So suppose your method has, okay, mobile pH should be 4. No, it actually works pretty well if it's 3 or 5 also, nothing. Then we can say that the method is robust regarding pH. But it can be non-robust regarding some other parameter. Yeah, maybe, for example, let's say some sample preparation nuance is very delicate, yeah, and you have to do really correctly in order to get correct. Now, ruggedness can be described or can be defined as characterizing method capacity to remain unaffected by small variations of extraneous character. these are things that you cannot really deliberately change, and that become very difficult to pinpoint what they are. It can be something like, let's say, room temperature, air pressure, skill of personnel, etc., or some, let's say, some general working culture in a lab, how glassware is washed, how often things are changed, replaced, maintained. So all those like fluid and strange. And robustness, you can easily like determine like by changing deliberately parameters. Ruggedness, not so much. Yeah, if there's a person, yeah, you cannot like adjust the person that today the person is very skilled and tomorrow the person has low skill. You cannot really do that, or you cannot manipulate laboratories working culture deliberately. Yeah? So ruggedness, the term ruggedness, therefore, very relevant if the method is transferred to another lab. So if in your lab the method works well, yeah, you've used it, and now you go to the other lab, teach those people how to do, and they start doing it themselves, and it works. Then you can see that it's a rugged method. Or if something like changes in your lab, suppose new people come and not so skillful, the new people try to do everything as is required. Yeah? They don't deliberately change anything. Yeah? And if still that works well, then it's rugged. But if new person comes, not really skillful, not so experienced, and sort of does everything the same way, but doesn't really work, then it's not rugged. But then again, in many cases, these both things are united into a single term, which sometimes is called robustness, sometimes ruggedness. How do you determine it? This is like with selectivity, ruggedness and robustness determination is not so easy to express with any one number or determine easily. What people typically do is they change parameters and observe the change in results. So this works especially well with this, as we defined it here, the robustness, maybe not so well with ruggedness. But now, how else can ruggedness and robustness be demonstrated? This how else is actually in part also the reason why I'm not putting more slides and more things here. Because ruggedness and robustness can be pretty well demonstrated or confirmed by also other activities which have been parts of our course, so that you know them well. Method development or optimization, Christian says. Yes, Christian, but not really. Yeah. Yes, you can optimize and develop, but you are still not, might still not be sure how rugged it is. Yeah. True, you can change characteristics and observe the results, but this is what I already said. My question is, how else? And I think Hans or Louis, who said interlaboratory comparisons, yeah? Perfect, yes. If you routinely participate in ILCs, proficiency, and always you are pretty good, yeah? Your Z scores or zeta scores are always below 2, absolute value always below. Probably it's rugged. And the same is analysis of CRMs. To analyze certified reference materials. So that although not directly called ruggedness demonstration, but interlaboratory comparison is possibly the best way to ensure that you are doing well. For reasons that I have explained. Yeah, it's completely independent. You have no idea what the analyzed value is. You simply do your work and then see whether it matches. Okay. And ruggedness and robustness are also directly related to measurement uncertainty. So that essentially, the less rugged or less robust is your method, automatically it has higher uncertainty. So that in indirect sense, measurement uncertainty evaluation, for example, with NORD-TEST, also characterizes indirectly your ruggedness. Because this long-term within-lab reproducibility, if it's not rugged, your results will vary a lot. If it's rugged, they vary a little. And agreement with reference values of CRMs or intercomparison, again, if they are a lot off, all this goes into uncertainty estimate and inflates the uncertainty. So that an indirect evaluation of ruggedness robustness also is measurement uncertainty. Now, today, again, we have to do shorter, so we have to stop now. I need to go outside Chemicum to completely different activities. We have few slides remaining from validation, and our next section will be quality assurance, or let's say quality assurance, or it's called, I think, control charts, because control charts are the main thing that we will be discussing. We will start with that tomorrow. Sadly, I haven't yet updated materials. I hope to do this evening. I want to do some changes there. Not massive, not big changes, but still some changes will be. So that, let's say, by tomorrow morning, it is safe to download the slides for quality control and or control charts. But now, the lecture is over, unless some last minute question. Luis?
I have just a little bit. We're calculating the CC alpha and the CC beta. They also have uncertainty, right? So when we were doing the Excel, I was thinking like the threshold was 0.07, I think, for CC alpha. So if it's down that, then we need to take into account also the uncertainty of that value, so it wouldn't be exactly 0.07.
I know it will not be exactly as I said. It's a very changey thing. You see, you are more than correct. Absolutely, they do have uncertainties, and they have big uncertainties. But it is, as far as I know, quite unusual to evaluate uncertainties of LODs or CC alphas or CC betas or LOQs. I actually haven't really encountered that this is done. So my advice again is redetermine on different days. Best you can do. All right. So thank you. Yeah. And we will meet again tomorrow.